unmute his microphone and ask a question without any problem.
Yes, yes. I mean, please. I mean, just speak up. As you may know from my past seminars and here at the university, you know that I like a lot like Blackboard talk and and be very interactive. So please, just interrupt me, speak up. Don't be shy. I really don't care. Even if I don't finish the talk, it's really okay. And so today I will be talking about how to use stars as a laboratory of physics beyond the standard model. And I wanted to give this talk here because, as I was mentioning to Arturo also, I think that it's a kind of, we can like merge our efforts of physics doing plasma, condensed matter, astrophysics, and particle physics to do some cool advance in science. And this is the outline of my talk. I will give you kind of a little bit of motivation of what drives me, right, and what my research in general. And then I will give you this fly-by-night introduction about plasma physics. And by fly-by-night, I mean by really like physical intuition, because you are much more expert than me, of course. And then I will talk about my works, also some work in progress, and how to use stars like the sun, white dwarf, and also supernovae, for example, to look for dark particle like axion or even dark photon, I will mention at some point. And then I will conclude. Okay, so these are just, I have just one slide about this, but I really want to stress why we do what we do, like why we really need to go beyond the standard model. Okay, we know that the standard model is a very successful theory, right? I mean, the LHC found out the Higgs, right? A lot of people say that the LHC didn't find anything. This is not true, right? We found out the Higgs. It's a very spectacular success, right? And we have a lot of success in the standard model, but still, and lucky enough for my PhD and my career in general, there are still a lot of open questions out there. First of all, for example, dark matter, right? Dark matter is something very fascinating because we know that almost 25% of the energy content of the universe is made of matter, so something with a mass that we don't know what it is, right? We know that it's out there, right? But we don't know its properties. We just know that he needs to interact very weakly and it needs to have a mass. Actually, there are also theory about modified gravity, for example, and you can listen to talk in which they try to explain rotational curves or other like experimental evidences, like with this kind of theory. But to be honest, I really think that they all have some troubles. For example, explaining CMB or like early universe more generally, while dark matter really can explain all the puzzles. Like in the it's very consistent. Then we have other puzzles like neutrino masses, for example. Why neutrinos are so small? The mass, why they are so small, right, as compared to leptons, quarks, etc. We also have matter-antimatter asymmetry, right? I mean, we have much more matter in the universe than antimatter. This is also the reason why we are here, right? If there was the same amount of matter and antimatter, they would just, annihilate continuously, right? We are very lucky that it's not so, but we would like to have a dynamical explanation for that. And the standard model lacks to do so, right? Because there is no enough, for example, CP violation or Baryon number violation to generate this matter-antimatter asymmetry. So really, there are a lot of really fundamental open questions in our universe. There are also more theoretical open questions, like the hierarchy problem. And one other theoretical, both theoretical and experimental open question that I would like to mention, that maybe some of you already know, but is not as famous like dark matter, is a strong CP problem. It's another open question in the standard model, and this problem is the following. So Stephen Weinberg says that whatever term you can write down in your Lagrangian, you should do it. You should write it down. Okay. So if you take like the QCD, and you need to write down a term also like this, where G is the field strength of SU3. Theta is just a dimensionless parameter, right? And so, the technicalities here are not important. The important thing is that if you look at this term in more detail, you notice that this is a total derivative, okay? Now, if you did some course, for example, about QFT and QED, for example, you may have met a term like FF dual, right? And they told you, okay, we can just forget about this because we can use equation of motion. We end up having not observable effects. Okay, and this is true actually for abelian group in infinite space, as Mimmo and Luca and Andrea knows. Like in finite dimension, this could be different. But generically speaking, for abelian group, this kind of reason in QFT is good. But then when you go to non-abelian group like SU3, like for strong interaction, then this is not true. And actually, this kind of operators leads to observable effect. So apart from technicality, what really matters here is that if you write down this term in the Lagrangian, right, and there are no symmetries, right, that prevent you to do so, then you predict a dipole moment for the neutron, okay? But you don't observe an electric dipole moment for the neutron. So this essentially put a bound on this parameter theta, right? So actually this calculation also was done. I mean, also Weizmann was involved. And then there has been a lot of theoretical effort, experimental effort, sorry. And then we just have a bounds. And why this is a problem? Why this is called the strong CP problem? It's a problem because we have a very small parameter that we don't understand why it's so small. I mean, if you think about it, this theta parameter is just a dimensionless parameter. Okay, so why should it be so small? So this is why it's a problem. It's called the strong CP problem. Strong because it's related to strong interaction. CP because if you write down this term here and you use the properties of epsilon mu nu rho sigma, you can notice that this term is CP violating. Okay, and so this problem was noticed for the first time many years ago, and a lot of people work on that. Wilczek, Weinberg, Pesay, and Queen, and there is a very elegant solution for this problem. That is also the reason why I wanted to introduce this problem. That is the axion. So this is a general way of thinking in theoretical physics. Whenever you have some number, some fine tuning, let's say, that you cannot explain, it's a little bit like in inflation. Whenever you have some small number, you will like really to have some dynamical explanation for this, okay, or some symmetry that explain this. So, and the axion does perfectly so. So essentially, what the axion does is you promote in this theory the theta parameter to be a dynamical field that I call this AX here. Okay, so now it's a field. That is the axion, okay? And this axion is a pseudo-Goldstone boson associated with a new global symmetry, okay? That is the Pesay-Queen symmetry, okay? Again, the really important part here is that you have a new particle into the game that solves the strong CP problem with a decay constant given by Fa. And notice that I told you that it's a pseudo-Goldstone boson. So you know that when you break a global symmetry, right, you will have like massless Goldstone boson, right? The axion is a pseudo-Goldstone boson in the sense that it acquires a mass through non-perturbative effect. And actually, the astonishing thing here is that you go to solve the strong CP problem, and you find out a very good Dirkmayer candidate, because it turns out that it's very easy to produce the right relic abundance for the axion to be the dark matter. Okay, and this is why there has been really a lot of effort, especially also in the last 15 years, to look for this kind of particle, because it can both solve the strong CP problem and also be a good Dirkmayer candidate. Now, from this coupling here, you see that the axion, so this new particle that you have into the game, has a coupling with the gluons, right, GG dual. The most important thing actually is that in the QCD axion case, you actually have also a coupling to photon. And this is why, and this is because essentially you couple to quarks, right? The quarks then are charged under electromagnetism, right? And so you end up also having a coupling of this type, okay? So now FF dual are the field strength of U1 electromagnetism, right? So now you have a coupling, a very peculiar coupling, FF dual, right? It's not like a dilaton coupling. If you would have had like FF, right? It would have been, for example, a kind of shift of the charge, right, of the electromagnetic charge. This is a very peculiar coupling, and the strength of this coupling is set by 1 over Fa, where Fa is the decay constant of the axion. Now, this was just to give you some theoretical motivation and why people like Weizmann, Wilczek, Weinberg got interested into this kind of problem, Pesay and Queen, of course. But at this point, actually, you can, for all the rest of the talk, you can just think about this new particle AX that I have in my spectrum of the theory that will be coupled to the photon in this way, okay? And you can call whatever is here, this alpha over 2 pi over Fa, just call it GA gamma gamma. So it's just a coupling. So you have a particle, axion, coupling GA gamma gamma to photon, okay? And this actually, more generically, this is also called an axion-like particle, because there are, like in many string theory, string theory with compactification, actually, you also have what is called this string axiverse. So you have a plethora of axion-like particle like this with this kind of coupling that pump up in your theory. So there has been a lot of effort theoretically and experimentally to look for particle of this kind, with this kind of coupling. Okay, and this is what I will be studying during this talk. So now I'm done with the presentation and all the particle physics stuff and the theoretical stuff. It was just to give you an overview of what we think. And now we'll go and talk about what you know more, I think, and actually you know much better than me. And is I want to give you an overview of the plasma physics that I will be using, okay? And I hope this can be useful, especially for people like particle physicists, because usually particle physicists, we think about particles in vacuum, right? Now, the issue is that if you are, instead of being in vacuum, you are in a medium, okay? Genetically speaking, the dispersion relation of the particle are modified by the interaction with the background medium. Okay, so for example, if you're in an isotropic medium, right, and you can write down the Maxwell equation in the Lorentz gauge, and it will be of this type, where this is the polarization tensor, okay, and that is essentially encapsulate all the properties of the medium in which you want to excite the electromagnetic field. And from here, you can notice a couple of things. So first of all, here the polarization now are 3. So usually you just have the 2 transverse modes, right? That here are the plus and minus. Now you have also a third polarization that is the longitudinal modes, okay? And this is because essentially whenever you have a condensed matter system, right? You're breaking Lorentz, right? So and the system as you have, if you want a new vector to play with to build your polarization tensor, it is the velocity, the quadrivelocity of your fluid, of your plasma. Okay, so you end up also having this kind of longitudinal modes oscillations just due to the presence of the plasma itself. Okay, and second of all, you can notice that for each polarization, you can solve this equation if you have the polarization tensor, and you can find your dispersion relation. Okay, so for example, for most of the talk, for all the talk, essentially, I will be interested into a QED plasma. Okay, so essentially just electrons, and what you end up with is calculating the forward Compton scatter at the microscopic level, right? What is changing the property of the photon is the fact that there are electrons, right, with which the photon is interacting, okay? And so actually you can compute the polarization tensor in an isotropic medium actually without parity violation, nothing weird. The 2 transverse modes are just the same. So you have these 2 polarization that you can calculate, and that depends on the properties of the medium itself. So here you have the distribution function, right, of your electron and positron in your plasma, right? And this will depend on the chemical potential, on the temperature of your plasma. And notice here that typically in a star, you will have like electrons, for example, and also ions, right, protons, for example. So when you calculate the index of refraction, right, you usually don't care about a proton, for example. And this is because...
Can I ask a question? About,
yeah, sure.
In this square bracket, this omega and k and v are do not depend on p? Or they...
No. They do not depend on p. But actually, if you're, for example, in the Lorentz gauge, so you're doing this integral in p, right, over the distribution of the electron. Then, in order to find the, let's say, the on-shell condition and the dispersion relation, you have to typically numerically solve an equation that is omega squared minus k squared equal all this stuff here. Okay, and so then you will just draw your dispersion relation in the plane omega k. Okay, but in principle you're just integrating over the phase space, and so p is a variable of integral, and then omega k is what you have and what you have to determine the dispersion relation, right? As omega change as a function of k, right?
Yes. The question was, k is equal to p here in this. Is just p? Is just
no. P is the momentum of the here, for example, of the electron, right? Here, while k is the momentum of the photon of which you want to find the dispersion relation. Okay.
And the square bracket has got a p dependence.
No, here the square bracket has no this p dependence here, right? It just depends. No, better to say the dependency is in v, because this is the velocity at which the electrons are moving. okay? But omega and k, they do not depend on p, okay? But in V, you have the dependence on the momentum too.
Thank you.
Okay, thank you.
Yes, good question. And actually this is also why, you have this integral, and in principle, this integral is not always easily solvable, right? You have to solve it numerically because you have this distribution, so the energy will be the energy of the electron, right? In which there is also, it depends on the momentum, of course. And then V is also the velocity of the electron, right? It will be close to 1, for example, when the temperature is very large, or in the tail in which the momentum is very large, right? But in general, you have to solve this numerically. There are limits that you can solve like analytically, and then you are actually the usual stuff. So this actually, I want to stress this because it is important to understand physically. So this is really the, let's say, the most general thing that you can write in this QED plasma. Then when you go to like plasma physics book or like even astrophysics book, right? What you find is more something like this. Okay, so for example, this, what I write it for you is the dispersion relation, okay, that you find solving, plugging in essentially those momentum tensor in the Maxwell equation, okay. These are the dispersion relation for the two modes, the transverse modes here above, and then the longitudinal modes, okay. Now, in the classical limit, so in the limit in which essentially you're, like in the sun, for example, you are in a non-degenerate and non-relativistic limit, okay. Now, forget about the temperature. It's not important for us. Forget about this piece of the temperature. So what this is telling you is the usual thing that people say in books, and it's true. Like they say, for example, then when you are in a plasma, right, the photon acquires a mass. And they say so because if you look at this relation, forgetting about the temperature, right, it's just saying omega square equal k square plus omega p square. Now, omega p square is the so-called plasma frequency, right, that I define here. It essentially depends on the density of the medium. And for the transverse modes, it precisely acts like a mass, right? Of course, this is not a mass. I mean, this I want to be like precise. It's not a mass. It's just a gap, if you want, in the dispersion relation. But we are not breaking gauge invariance, right? We are breaking Lorentz, but we are not breaking gauge invariance. But Lorentz is okay to break Lorentz if you want. I mean, every condensed matter system does, right? Even the chair that I'm sitting on, right, is breaking boost, is breaking rotational invariance, right? So that's okay. And then there is also the longitudinal modes. Again, if you forget about the temperature dependence here, right, then you have that the longitudinal modes are just oscillating with a fixed frequency, right, that is given by the plasma frequency. And these really are the modes that they just disappear. They are not there if you are in vacuum. If you are, omega plasma goes to 0, it means that essentially the density vanishes and you don't have it. And also kind of like just to speak about names, usually people talk about photons when you are talking about excitation of the electromagnetic field in vacuum, right? Well, if you're in a medium, like in this case, you talk about plasmons, but still it's just the excitation of the same field, okay? Just in one case, in this case, you're in a background, okay? So, and this is important for all the idea that I will be discussing. So this is the dispersion relation that you see in the plane omega and k, okay, normalized with the plasma frequency. I fix some temperature here as just to give you an example. So this straight line, of course, is just omega equal k. So this is the photon dispersion relation in vacuum, okay. Then here you have the transverse modes, okay, with some kind of massive photon with this plasma frequency. Then you have the longitudinal photon. It is just flat for low enough k, okay? And then what I draw here is the dispersion relation of a massive particle that I call axion, my axion, okay? Where this capital K is just the quadrimomentum K, right? So it's omega square minus k square, okay? And so with a small enough mass in scale. So the important thing that you have to notice here is that if you draw this line of the axion momentum, the dispersion relation, there is always a K at which you have a crossing between the axion and the longitudinal dispersion relation. So this is what like actually stimulated us in order to study this. Whenever you have some resonance condition, you can enhance production, you can enhance processes, right? And so we started to think about this and started to say, okay, maybe we can convert longitudinal plasmon, right, into axion in some environments, okay? And so this is what we did. in a couple in 2-3 words that I will be talking about. But just before going to this, I wanted to remind you which was the coupling that we are studying. Okay, if you remember, the coupling was axion FF dual, right? So, like poorly speaking, will be axion coupled with 2 photons. Okay, so essentially, what I will be doing is to convert a longitudinal plasmon that you have, for example, in the sun, into an axion in the presence of an external magnetic field, because we know that in stars there are actually strong magnetic fields, right? So we can use an external magnetic field as a source to pump up the conversion to axion. Okay, and so actually there is a very elegant way to calculate the production of particle from a thermal plasma. So this goes back to Weldon, and actually I'm sure that Mimmo, Luca, Arturo, Andrea, they know this kind of papers. Andrea, I mean, much better than me. But essentially, within thermal field theory, you can calculate the rate of emission of a weakly interacting particle very easily. So if you have a thermal bath, right, with some temperature here T, right, and you have some weakly interacting particle with this bath, it can just escape freely, like the axion. Okay, you can calculate the production rate just calculating the self-energy of the axion into this external magnetic field and taking the imaginary part of this. Okay, and so with this, you can actually calculate very easily, for example, which is the production rate of axion into a star. Okay, and this is the associated energy loss. Let's just understand the physics. Actually, if any student is also interested about all this calculation, I have some ordered note in which I derive everything, and I can share with you if you like. But for the moment, just explore this formula here. This is the energy loss. What I mean by energy loss is that imagine that you are in the core of the sun. Just take the sun as an example. This is the one that I will discuss. Now you have a lot of plasmon. Some of this plasmon, because of the presence of this of a coupling of this vertex here, Ga gamma gamma, right? They can convert and produce an axion, but the axion then will be very weakly interacting, so it will just escape freely from the star. Okay, so essentially this will accelerate the loss of energy, will enhance the luminosity, if you want, also in this kind of particle, and so will accelerate the energy loss of the sun. Okay, now the energy loss depends on what? At a given radius, it depends on the magnetic field. The larger is the magnetic field, the larger will be the production rate. Ga gamma gamma, remember, is this coupling that enters the vertex here, is the coupling between axion and photon.
Andrea, can I ask you a question?
Yes, sure.
But I didn't understand which particle is losing energy in this process.
Good. It's not the particle, is the sun that is losing energy, in the sense that you convert. Imagine that you have this plasmon in the sun, right? Just plasmon in the core of the sun. Okay, just photon excitation of the electromagnetic field. So they, of course, they interact very strongly. So they stay there, right, in the plasma, right, because they interact through electromagnetic forces, right, and with all the electrons and whatever, right. But then at a certain point, if the B field is large enough, and if this coupling Ga gamma gamma is large enough, they can convert into an axion. Okay, at that point, the axion just will escape from the sun, okay, and will escape with this energy. Actually, this is a good question, because also, you remember this plot here, right? I told you that there was this crossing between the axion and the longitudinal plasmon. What this means is essentially that imagine that you have a longitudinal plasmon with an energy that is given by the plasma frequency. Okay, for example, just to give you some number, in the center of the sun, the plasma frequency is around 0.3 keV. Okay, if you have a large enough coupling, Ga gamma gamma, you can, and you have a large enough magnetic field, you can resonantly convert this plasmon into an axion, right?
Yes.
Because here you match. And so what you will end up with is essentially expelling, if you want, emitting an axion with an energy equal to that of the longitudinal plasmon of omega plasma frequency, because that is where you get resonantly enhanced. Okay? And so essentially, at the end of the day, you are emitting axion with an energy given by the plasma frequency, and you are losing it because they are just very weakly interacting.
You are losing longitudinal photons.
Exactly, and so you are cooling down. Actually, here we are doing it with longitudinal photon, but people do it also with transverse photon for what is called also Primakoff effect. And actually, this is how people look for axion, dark photon, and this is also stimulated because there are anomalies in astrophysics. There are cooling anomalies in stars like horizontal branch, like white dwarf, in which there is a cooling. I mean, if you think about it, if I ask you this question, right, what is the other particle that can compete with the axion or like weakly interacting particle in losing energy to the star? The only other particle essentially is neutrino, right? Because neutrino can then escape freely and they interact very weakly, okay? So you can calculate the rate of cooling that you expect from neutrinos, okay? Then you go and look at data, and then you see that the cooling is much faster, right? Or like different. And then you can say, okay, maybe we are losing something. Maybe there is something else that we are emitting and that we are losing energy with. And this is also what stimulates looking for this kind of new weakly interacting particle, okay?
Okay, so this for energy loss is energy loss of the star.
Of the star, exactly. In fact, for example, I will talk about this in a minute, but the most naive bound that you can do is, okay, let's look at the total luminosity of the sun, right? So a very naive bound that I can put with this relation, I can integrate it over all the star, and I can impose that the luminosity via this process has to be smaller than the luminosity of the sun that we observe, right? Otherwise, would be just inconsistent.
Excuse me, this is energy loss per unit time, correct?
Yes, right. Like now here we can check the units, but here is like, let me do it at the moment, like here is electron volt 4, 7, yeah, it should be so per unit volume also, right? Because then for unit volume, because then I will also integrate over all the star, right? And remember also this, if you want to check the dimension, the GA gamma gamma has dimension. Because remember, when I put in the axion field, I started with a dimension 5 operator, but then I plug in a field, right? So my dimensionless parameter became a scalar field of dimension 1. So GA gamma gamma has to be dimension 1 over energy. Okay. So now you're losing energy. Okay, and this formula is kind of general. We can apply it to different sources, different stars. To be fair, I will be talking first about the sun and white dwarf. I don't know if I will be able to talk about supernova, but it's really not important. And so let's talk about the sun also, because here, I mean, the university here is very strong on the sun side. So I will be glad to discuss about this. So why the sun? Of course, the sun is the closest star, right? Is very good to look at it. And if you just look at this formula that I actually didn't explain very well, but I didn't finish to explain. Another important thing is that it depends on the magnetic field, right here. It depends on the plasma frequency. So the plasma frequency depends also on the density, as you may remember. And then it also depends on the temperature, right? Here you see the statistical factor. Actually, this, like, physically, this is very easy to understand, right? You want to convert longitudinal plasma, right? But in order to do so, you have to have a population of them. Okay, so actually this is very important when you do some back of the envelope estimate to see if your process can be important. You have to check that you have a population to convert. So for example, if the plasma frequency happens to be too large as compared to temperature, then likely it will be very hard to look for this process, because you will be, let's say, kinematically exponentially suppressed. Okay. That said, essentially, this formula makes very compelling the fact that we really need to have information about the properties in the star. Okay, so for example, for the sun, what we did was to take the Sackley model, that is one of the model for the interior of the sun. So we have here the plasma frequency, we have here the temperature, we have also here, maybe I don't know if I will have time to discuss this, but the D by screening length is not important for my calculation. It's important for other processes that people consider for the axion. For the moment, I care just about the plasma frequency, the temperature. So the plasma frequency in the core, for example, as a function of the radius, right? So this is like 0.3 keV, more or less. The temperature is around the keV. Actually, I don't know if you ever noticed this, but there is a very physical intuition why the temperature in the sun, and most of the stars is always very similar, right? It's always around the keV, right? And this is because essentially normal star, you can just apply virial theorem. They all have kind of the same mass. So if you just take a proton, right, at some radius of the star, and you use virial theorem, right, you end up having a temperature around the keV. Okay, there's actually, so it's just a back of the envelope of what temperature you should expect for a star like the sun. Okay, and
so in these graphs, you have a temperature as a function of the distance from the center.
Exactly. So you see that in the center, for example, is larger, and then it just goes down when you go to the external layer. Exactly. Okay. The radius of the sun, the radius normalized to the radius of the sun. Exactly. Same for the plasma frequency, and also for the debye screening, that actually depends on both the electron and ions. Okay. And then maybe, you know, if there are experts here, they know that there are some uncertainty about the decomposition of the sun. The most compelling one is the chemical, actually there is a chemical abundance problem, right? So there is some uncertainty about the chemical composition of the sun. At the end of the day, all the different models for plasma frequency and the temperature have an uncertainty that is few %. So for us, it's really not important. What's really crucial for us is the magnetic field structure. So what we adopt here is actually this benchmark model used in this paper by Kuvidat et al. And also in a following paper like 6 years later with other astroseismology data. And essentially what they have in this model, they divide the sun in 3 parts. So they have the internal part of the sun that is called the radiative zone, in which the magnetic field is very large. Okay. Then you have the Tackock line, in which that is essentially a very thin zone that separates the region in which there is uniform rotation from the region in which there is differential rotation. And then there is the upper layer, and of course the magnetic field just increased toward the center, right? And then it's very small in the external layer. And so we use this model, but of course this is a huge uncertainty, and I will tell you what we hope that we can do maybe in the future. But just to go briefly over some calculation, like here, for example, we took, if you take the energy loss per unit volume, right, also per unit time that we were like calculating that, and you integrate over the sun, you estimate, you have the luminosity, right, in watt, as Andrea was noticing, and then you can compare this luminosity with other processes that people consider. Okay, so for example, usually if you listen to a talk about axion in the sun, they will always talk about Primakoff. What is Primakoff? Primakoff uses essentially the same coupling that I will be using, but instead of converting a longitudinal plasmon into an external B field, you convert a transverse modes into the field of the ions essentially in the star. Okay, and actually people consider, and we were the first one actually that considered this longitudinal plasma, and there was a good reason, in the sense that if you compute the total luminosity, the Primakoff wins. So the Primakoff is in blue, and the red are our computation for different kind of model. The one that you should look at is the solid line, is the model based on data, that fit the data. And then you can see that the luminosity is smaller, so one can get depressed. It's very sad. But then you realize, this is a suggestion. You know, whenever you measure you calculate something like this, right? And you in stars, and you calculate the luminosity. The second question that you should ask yourself is, what is the differential flux? Okay, so then you can compute the differential flux. So this is the differential flux as a function of the energy of the axion. So remember, what we are doing is converting plasma to emit axion. Okay, then I will talk also how we will detect this axion. But at the moment, we are just emitting axion. So this is the differential flux as a function of the energy in keV of the axion that we are producing in the sun. Okay, now the blue differential flux is the Primakoff. So we recomputed it. This is a standard result in the literature. And you can notice that it's peaking around 3 keV. This actually should not be surprising, because it's a thermal process. So essentially we'll peak at 3 times roughly, like around the temperature of the sun. Okay. Now, the most important thing is the red one. Now, the red one are our processes And I think this plot is very beautiful because from this plot, you can really see the structure of the sun. Why so? So the first piece of the plot here is essentially all the axions that you are producing in the radiative zone. So you remember here, we have this internal zone, right? Was the interior part of this magnetic field model. So you can understand why the peak is larger, because the magnetic field is larger there. It's around 1,000 of Tesla, so it's large, okay? And then you can also understand why it's peaking at large frequency, okay? As I told Marco before, essentially, you are producing axion at a frequency that is given by the plasma frequency. So if you are in the central part of the sun, the plasma frequency is larger because the density is large, okay? So this essentially, you are seeing all the axion that have been produced in the center of the sun. Now here instead, in the second peak here, you see all the axion that have been produced in the Tacock line. So you see that the region is very small because in this model, the Tacock line region is very small. The peak is smaller because the magnetic field in this region is smaller, and then also the frequency is smaller because you're in an external part of the sun. So the plasma frequency gets down because the density, of course, goes down when you approach the surface of the sun. And then this little bump here is the external layer. So it's even smaller than before because the B field is very small. And the frequency essentially are close to the visible light. It's mainly visible light because you are very low density, so very low plasma frequency. And here, as an example, we also computed the axion flux that you would expect from just the internal part of our planet, of the Earth. Okay.
Sorry,
yeah.
Andrea. Just understand better this figure.
Yes.
This figure is depending on some parameter that has to be fixed from possible future measurements.
Right.
Yeah. What are the parameters?
Yes. Yes, exactly. So in the next slides, also I will talk about also how we will measure this parameter, how we hope to measure the axion. Right. At the moment, in this plot, what we did was to fix that GA gamma gamma. Okay. Notice here that once that you fix the axion model, okay. Once that you fix the solar model, the only parameter that you should really fix is the coupling of the axion, right? Because the mass of the axion is always very small for the model that we are interested to, typically. And I mean, smaller, for example, the Kiwi. So don't care about the axion mass, but we care about GA gamma gamma. And as you are pointing out, GA gamma gamma fix the strength of this emission, okay? So essentially, this plot is made assuming the GA gamma gamma at the border of the actual exclusion plot that we have. And I will show you in a moment how we have this exclusion plot and how we hope to measure it in the future. Okay, but essentially.
But this I understand. Sorry if I trivialize the question, but this is an optimistic estimate, or so could it be also smaller if GA gamma gamma is smaller?
In fact, yeah.
Okay.
It could be smaller if you, and then in some sense you will put some bound on the combination GA gamma gamma magnetic field. Exactly.
And do not depend on the mass?
No, if the mass is, so there could be for example, here, right, there could, or even here, you can see some drop, even just some kinematical cutoff. If the mass starts to be, let's say, similar to the plasma frequency, actually you have to care about maybe transverse modes, okay? Because you remember the transverse modes as a dispersion relation, omega equal K square, omega square equal K square plus omega plasma square, right? So for example, when the plasma mass starts to be similar to the mass of the axion, or better to say vice versa, maybe you have to consider that one. But here you should see some drop off because if the mass becomes too large, then essentially you don't have enough energy, right, to produce it. But until the mass is below, electron volt, let's say, that is actually what is usually motivated for the QCD axion, then the mass, you just don't care about it, right? Right, that's correct.
Andrea, may I ask another question on this plot?
Sure.
I'd like to understand, why do you have 3 separate peaks for these red curves? I mean, the magnetic field in the sun should be continuous. Why do you have these clearly separated peaks?
Yeah, the point is that the magnetic field, the magnetic field is not continuous. So essentially, basically, so I'm not an expert, of course, of that type. So we on that side of like simulation, etc. But basically, what they did in this paper was to really separate the magnetic field in 3 different regions, and there is some gap between region, probably due to like rotational effect and some weird turbulent stuff that I'm not really the most expert to explain. But really, this separation is not an artifact of my numerics or nothing. It's really the model that they are using to fit the speed of sound, to fit the abundance and the temperature of the sun with this model, and not to screw up the neutrino emission from the sun. So it's really a model that they have with this separation of the 3 different regions.
So sorry, which is the main process that generates such a big field? Because in solar physics, this is very weird and rare thing.
Right.
This kind of modeling of the magnetic field inside the sun. We know barely what happens in the convective zone.
Exactly.
Through the convection, through instabilities and hydrodynamic instabilities, if you want, turbulent instability. But really, in the radiative zone is really a big question mark.
I agree. In fact, I think that is also why this can be interesting in the future, in the sense that, as you said, so to be honest, what they do in this paper. So first of all, in this paper, they were doing 1D simulation. Okay. So how they add the magnetic field is not that they. This is a good point. It's not that they like motivate this magnetic field or this. What they do is just they add a term to the pressure, right, due to the magnetic field and to the Alphen velocity, right? And they try to. Right.
But that's crucial because we actually in solar physics, people do not even assume that there is a magnetic field inside there.
I agree. In fact, I agree. In fact, I will in the next slides I will say that how these. So the first paper that we did was kind of more theoretical, right? To say. It could be interesting in the sense that usually, as you said, in a lot of, in general, you maybe not have the magnetic field in the sun, right? Or maybe can be there. For example, you do have bounds, right? For example, you have bounds from the oblateness of the sun, right? That gives you a strong bounce on the magnetic field. Like it has to be like smaller than 6 × 10⁶ Gauss or so in the radiative zone. Otherwise, you would have changed the oblateness of the sun much more than the one that you measure, right? But as you said, it's very difficult. And also neutrinos, for example, they do not give us, given that they are very sensitive, their production is very sensitive to the temperature, right, in the sun. They really not give us a lot of information about the magnetic field, as you say. That is really a crucial point. And this is also why, so this is like doing this assumption, right? And then the most interesting, and also what...
Andrea, the neutrino flux is not included in this picture, is it?
In the picture of the paper of the magnetic, so here in this picture here of the axion, I mean here I didn't report right the neutrino sun. Of course they do take into account, and actually in the model of the on the solar model of Huidat et al., one of the main goal of their paper, actually, in which they also play a lot with other parameters like the metallicity and other parameters of their simulation, is actually to better fit the neutrino flux and to better agree with the prediction and the measurement of the neutrino flux from the sun. But here I'm talking about axion.
Is it a way of solving the neutrino flux problem, adding these actions?
This I wouldn't say so, to be honest, for the sun. No, because actually, no, I mean, with the actual parameter, you can solve, for example, this problem maybe in other stars, but with the sun, I really don't think so. Right? Yeah. But that's also, I mean, this also brings me, I mean, it's also related to the previous question and or comment that was a really important one, and actually brings me to the other. And so about this, we did this work with my. I just want to make some propaganda also for my collaborators, Alex Miller and Eduardo Vitagliano. Actually, Eduardo is from Naples, and now he's in UCLA doing a postdoc. So we did this paper because people overlook. We did this calculation, and people didn't consider this. And then we were actually approached by someone working on axion detection. And now I will just briefly say how people try to see axion from the sun. What we did was in this paper was to consider what would happen if you have this strong magnetic field in the sun. And actually this is crucial what has been said. So first of all, let me explain you what is a Nelioscope. Okay, so YAXO, that I call it, you know, that I write here, is what is called a Nelioscope. Okay, an helioscope is essentially so you are on Earth like CAST. CAST, for example, maybe you heard about this experiment looking for action that is called CAST. It's actually operating at CERN since many years. So essentially what you have is this very big magnet, and you point this magnet towards the sun, okay? Now, imagine that you emit, because we have produced it somehow, you emit the axion from the sun, okay? Then you point your big magnet to the sun, okay? And then what you expect is that if there is an axion flux coming, you should convert back into X-rays, okay? Why X-rays? Because of course we will be peaking more or less at this frequency here, right? So actually people in CAS, they were thinking mainly about Primakoff. They completely missed this flux, but Primakoff is independent of the magnetic field. So this actually replies also to the question by Andrea before. So if you calculate a Primakoff, this just depends on the GA gamma gamma at very low mass of the axion. So what people do is that, okay, we produce the axion in the sun. If we produce the axion in the sun, then we should be able, if GA gamma gamma is large enough, we should be able to see X-rays produced, okay? And so they don't see any X-rays, so they put a bound, okay? And just an highlight of how Helioscope work. So just the main physics. You have an axion flux in the sun, okay? So in our case, for example, you have a solar model, you have the axion flux of two types, the Primakoff and our flux. You depend on GA gamma gamma and the mass. If the mass is very small, just ignore the mass. Then the axion flux arrives to the Earth, okay? It's the helioscope, in which there is a long, like meter scale or larger like detector with a strong B field, okay? And it converts back into photon, and then you see X-ray, okay? So essentially, at the end of the day, what you have is that you have a flux of photon, okay, in your detector. I mean, you should have, if there is the axion out there with that coupling GA gamma gamma. For example, these are to be fixed like 10 to minus 11 GeV to the minus 1. And you see that before us, people were considering just this curve, okay? And then if, and there is a big if there is a strong magnetic field, then you should see also this peak here. Now, I go back to the question that was, to the comment that was made before. And it's completely fair in the sense that we really don't know much about the internal field, magnetic field in the sun. We really don't know much either about the internal magnetic field, for example, in white dwarf. You know, we can see the external magnetic field in white dwarf with Zeeman splitting, right? But we don't know what is happening inside. It's very difficult to probe the inside of a star, right? Even with neutrinos, it's very hard. Now, in the case in which we detect the axion with some experiment, right? Then axion can really act like neutrinos. So they can really give us information about the internal structure of the stars, about the universe. I don't have to talk about here about, you know, how they can affect CMB or whatever, but they can really do this. So I completely agree with the first statement made before, but you know, it can be really interesting to explore like the solar interior in the case in which we find out the axion. And I'm not saying that we need to find out the axion, but I also wanted to highlight why people around are also excited about the axion, and in general they keep looking for it. For example, last June, you may have heard about this anomaly that has been detected by the Xenon, mostly Italian Xenon collaboration. Okay, so Xenon is an experiment that looks for dark matter through electron recoils. Okay, and last June, so June 2020, they announced an excess. So they see an excess essentially at a low, in the low beam between like 2 and 4 keV. If you want to know more about the physical explanation about this excess, you can look at this paper that I did with this bunch of folks, like for example, like Tomer Volansky, that is my boss in Tel Aviv University, in which we put under scrutiny a lot of possible explanation, and it actually it doesn't need to be dark matter. For example, it could be some particle.
Andrea,
yes.
This is an excess of what?
In excess on events. These are the events rate of these electron recoils in the S1 channel It is the one that they detect with this electron recoil in xenon collaboration. So they have some some background modeling, right? And then they see an excess over that modeling by 2.5 sigma. So it's nothing definitive. Otherwise, it would have been much more excited. But it was an excess in the number of events seen at between 2 and 4 keV. So here, as you can see, and this actually stimulated a lot of interest in physics coming from the sun, because as I told you before, when something is around the keV, you immediately think also about the sun, right? Because the energy is that one. At this point, we really need more data, right? Because it can be really like tritium background, for example. We really need more data. We also need maybe a better understanding of the background, okay? But just to tell you that this also stimulated even more interest for axion, dark photon, or stuff emitted from the sun. So if this, for example, turns out to be true, right, and you start measuring the axion, detecting the axion, then this gives our process access to the solar interior in the magnetic field. Okay, so there is really a lot of activities and a lot of experiment going on all around the world. And so I think that is, and there is a lot of physics. Really,
so in this paper, you are claiming that this electron excess is due to interaction with axions coming from the sun.
No, actually, in this paper, we are analyzing different sources. If you take the vanilla model for axion, actually, there is a tension with other solar constraint, like, other star constraint, like red giants and horizontal branch cooling. But for example, in this paper with Itai, Ruven, Diego, we propose a model in which, for example, you can have an axion and that can explain the excess, avoiding other stellar cooling bounds. But we don't talk, I mean, in this paper, this actually was a crazy paper in the sense that it's like 50 pages long. Usually, when you have this kind of excess, you see immediately paper of, 4 pages, 5 pages. This was really, I didn't sleep for 10 days, essentially. But it's really 50 pages in which we studied we did all the statistical analysis on our own. And we studied also the axion case, but also the scalar case. And it fit well the data. So the fit is good from the sun. The point is that there are some tension then with other data from mainly horizontal branch and red giants with axion, right? Yes. Okay, is there any other question about, because actually I'm running out of time. I don't know, do they have other 10 minutes or shall I stop here and take question? How do they?
No, I think it's okay, 10 minutes.
Okay, good. I want to, of course, interrupt me also if there are any question about this other thing that I discussed. I wanted just to also to give you another, give you the example of another system in which actually more than the sun, there are hints that there are very strong magnetic field, and these are the white dwarf. Actually, we observe a lot of white dwarf, not a lot, 1/10 of white dwarf with very strong B field, okay? So this actually is a very good system to look for this process. Here I wanted to give you, with a blackboard would have been much better, but here I wanted to give you just a fly-by-night, like a very back-of-the-envelope estimate of stuff in a white dwarf. And because I actually, I could be teaching a lesson about this because I find this very interesting, like doing back-of-the-envelope estimate, right, to get the numbers right. For example, if you take a star, right, you can estimate the gravity pressure like just simply like this, right? Just a force divided by surface, okay? Then you can actually also, in a white dwarf, what you have is that the temperature, it goes like very low, and you have essentially, you are not fusing anything else, you just have electrons, and then you have the degeneracy pressure that counterbalance the gravity pressure, okay? And just by dimensional analysis, you can calculate what is the Fermi pressure. And I think this is very fascinating because you see really that it's really just quantum mechanics, right? Playing the game on astrophysical scale, right? So I think that it's like in inflation, right? The large scale structure of the universe is originated by quantum mechanical fluctuation, right? It's very fascinating. Also here, essentially, a white dwarf is sustained by quantum mechanics and gravity, of course. So, but the nice thing that I wanted to highlight also is that if you just do this back on the envelope, I can pass you the slides. you can write down the Fermi pressure, and the equilibrium condition is just the gravity pressure equal the Fermi pressure, right? And then you find a very peculiar relation. The radius is inversion, goes like 1 over the mass to the 1/3. So the more massive is this. So essentially, what you're saying here is very weird, right? The radius gets shrink when the mass gets larger. Usually, if you take a typical star, it's the opposite, right? And so this is very peculiar of the white dwarf. So the density increases here, and when the mass gets larger, while it's the opposite in the other star, and I mean usually, and actually always with the back on the envelope, you can also when the mass starts to be very large here in this back on the envelope, right? I was using a non-relativistic approximation for the energy, right? If you got very large mass, actually you should put the relativistic energy here, and you get in trouble if you try to do so. Here you get essentially the Fermi pressure has the same dependence on the, actually this should be r to the 4th, but are the same dependence on the gravity pressure. So the radius just, cancel, and then you cannot balance it. And this is a signal of what Chandrasekhar found out. That is a Chandrasekhar limit. So you cannot have a white dwarf that is too massive, that is more massive than 1.4 solar mass. And this you can really just calculate it with few lines, starting with quantum mechanics and back on the envelope gravity. Okay, so but after this introduction, this is just to tell you that the white dwarf is a very simple system that is sustained by pressure, the degeneracy pressure. Okay, and actually is mostly isothermal. So here, for example, you see this temperature, like the temperature of profile of the white dwarf as a function of the radius, and you see that it drops very, very slowly. Why so? Because I mean, essentially, the heat in the white dwarf is transported by electrons, right? And you can calculate that they have a very large mean free path, and essentially they can transport energy in a very efficient way. It's like being in a piece of metal, and so it's mostly isothermal. Okay, this is the plasma frequency that is much larger than the sun because the density is larger. And so here we are using this model that was given us by a group in Barcelona, Crico and collaborators, in which they have a model to match astroseismology data from white dwarf. And then what you can do, you can calculate the same process of before. And here, for example, is the emission rate as a function of the radius normalized to the total emission rate. And this is just to explain, is just to tell you that essentially the process is the same, always longitudinal plasmon converted into axion. But most of the stuff is happening into the external layer of the white dwarf. And this is because in the internal layer, the plasma frequency is very large, and the population of plasmon is exponentially suppressed. So you really cannot convert. Okay? And then, as I said before, as compared to the sun, we know that there are magnetic white dwarfs that have very, very strong magnetic field. Okay, in this case, there is another process that you should take into account. If you have a coupling to electron, you have to consider Bremsstrahlung emission of axion. Okay, and actually notice that if you have a coupling to photon, at one loop you will also generate just one loop. Just do one loop, and then you will have also a coupling to electron, right? So you will also generate a coupling of this type. So you have to compare this process for the emission of axion with our process. And this is what we did. And then we find that essentially, depending on the density and the magnetic field, our process can be also larger in this region, for example, than the Bremsstrahlung that usually people consider. Okay, people usually just ignore the longitudinal plasma conversion, but depending on the magnetic field, it can be actually very important and should be taken into account. And actually, there has been a very nice paper on this by these folks here, by Chris Dussert and Ben Safdie, actually from Michigan University and Berkeley University, in which they did observation. So they take some. So what they looked for was you produce the axion. They were looking for production through this Bremsstrahlung. Okay, so imagine that you produce the axion in the interior of the white dwarf. Okay, then in the external field you convert them back, right? And so what you would see is an emission in an X-rays. So what they did actually was to take some data from I actually don't remember which X-ray telescope, but an X-ray telescope that was pointing to this magnetic white dwarf for different hours. Okay, so they have some data, and then they analyze it, and then they found some bounds on the combination of GA-EE and GA-gamma-gamma. In our case, we would have a bound just on GA-gamma-gamma, but that depends on the magnetic field. Okay, and here I also want to stress that this is my view. I feel that all these things is not really important to set bound, because as also was mentioned before, like it's not so exciting. Also, as was mentioning before, we really have a lot of uncertainty in the magnetic field, but this could be a very good place to look for anomalies. And there are anomalies on stellar cooling and stellar emission. For example, there has been observed an anomaly in the X-ray emission from neutron stars. So, when it's a good place to look for a signal. Okay, if you then don't find the signal, maybe it's difficult to put a robust bound. But then if you do find the signal, then things get very interesting. Okay, and people like Ben Safdie from Berkeley and Tracy Slater, they're working a lot on like MIT. They're working a lot in this direction. Okay. Okay, so I will stop here because the last part of the talk doesn't add anything. It's just another example with supernova. So let me conclude. I showed you some physical. I hope that I showed you some really physical process happening that can happen in the sun or white dwarf or supernova that can actually test and find out particles. I talk about the axion. Really, you can do this for other motivated particles like scalar or like dark photon motivated by other things like string theory or other models, right? And you can really test it. But I really think that it's important to have interplay between astrophysicists, cosmologists, right? At the moment, for example, the supernova process that we are writing the paper, and we are working with a group in Japan that is doing 2D simulation of supernova explosion. And I really think that can be done a lot of cool stuff if people just speak more, right? I mean, there is a video on YouTube by Murray Gell-Mann 20 years ago saying that he would have wished more interplay between particle physicists, astrophysics, and cosmology and condensed matter. I mean, condensed matter physicists already, there is interplay, actually. A lot of concepts of condensed matter physics that were applied to particle physics. But I wish there could be more interplay between these different fields. And so now I stop here, and please, I am happy to take any other question that you may have.
Okay, so let's thank Andrea for his nice talk. And okay, are there any questions for the speaker?
Yes, Andrea, sorry,
yes,
it's Luca. I didn't get how the temperature of the white dwarf is affected by this action dynamics.
So the temperature, you cannot really measure. I mean,
the profiling temperature, I mean.
Right, the profiling temperature that I'm using is not affected by this, in the sense that it will be, I mean, on long lines, like long, let's say, time scale, you can see a variation of the luminosity, right? But the temperature in the star, given that this particle emission is usually very weak, right, is usually not affected by it. And also, usually in a star, you really have time, even if you change a little bit the temperature, to adjust a bit the radius, etc., in order to recover thermal equilibrium with a slightly different temperature, maybe, right? So that is not really the big issue. But you may be right in the sense that, for example, another interesting thing that people do, I mean, what I'm doing here is that I'm taking a white dwarf model with a plasma frequency, a temperature, right? And then I'm saying, okay, what happens if there are actions on the top of this model, right? But of course, you can really also modify the simulation at the first place to include the action.
Exactly, that's what I was meaning. Yes.
And people did that, right? Exactly. And a lot of bounds also are placed in this way, with, for example, horizontal branch and red giants, putting action in the simulation, so you have extra cooling. So you maybe modify, but you always, at the end of the day, you always modifying model the profile temperature, like maybe the lifetime, right, or other properties like the luminosity that is, as you said, also then related to temperature, right? And so that's a very good point. But then that requires like modifying, for example, all this, for example, MESA code, in which you can put an extra source of energy loss, right, in your code, very simply, and then you do the game, right? Yeah, that's correct.
Thank you.
Yeah, thanks for the question.
Let me ask Andrea.
Yeah.
Because you have a finite size object, your star, wouldn't you expect the longitudinal and the transverse mode to mix up?
Yeah.
Does this have consequences with the coupling?
That's a very good question. So actually, we checked that also. This could have been actually very dangerous, for example, for supernova, in which the density and the magnetic field are very large. So actually, the mixing between transverse and longitudinal modes could be actually very effective. It turns out that at the end of the day, for the system that we are analyzing, even if you are in a kind of, it's finite, yes, but it's kind of diffuse, like plasma, right? Then at the end of the day, these effects are not important. But in principle, if you do have a system in which they mix, they could be super, super interesting to study. I agree. And this could mess up everything. Yeah. So for example, this is also why when people do, a lot of people do also stuff with metamaterial and plasmon in laboratory, and there you should be careful what you couple to, what you're doing, what you're converting, and that's actually will be something very interesting to study. I mean, we were working on something completely different, but in this direction, right, of studying some of kind of finite system in which you can couple to this axion would be very interesting. But in stars, you don't have this issue usually.
Thank you.
Yeah, thank you for the question.
So are there any other questions? To some curiosities, also comments.
Yeah, let me say also that if you have any further question, you can just email me, or if you have any other thing that you want to check, it would be very nice to do so. I had a very nice conversation a month ago with Oresta, for example, talking about possibility of looking for neutron star, like magnetosphere. What happened to the magnetosphere of a neutron star if you have this coupling? And let me stress again that this is not just limited to axion. You can have other particles that are motivated. For example, another example that I could give you is millily charged particle. Recently, there has been a lot of interest, even paper published on Nature, about millily charged particle because of some anomalies in astrophysics, 21 centimeter, for example. And it would have been interesting, for example, to see how, if you add a millily charged particle into your solar model, right, apart from the electron, right, with some small millily charge, how that would affect the evolution, for example. So there are really, I think, very cool things that one can do. So I will be very glad to speak about it.
Okay. So if there are no other questions, we thank again Andrea for his nice talk, and I say goodbye to everybody.
Okay, thanks a lot for the invitation, and ciao ciao.
Ciao.
Thank you, Andrea. Bye.
Grazie a tutti.